Hello guys, welcome back. Dr. Manis here. Today we're talking about electrochemistry. In particular, just going to introduce you to galvanic cells. Galvanic is the root of galvanization. If you know what galvanization means, because you've dealt with some metals and stuff, great. If you don't know what it means, great. Really doesn't matter. Hopefully you do know what oxidation means. Oxidation and reduction reactions are the root of all this. I gave you an example of an oxidation reduction right there. In there, we have two half reactions. We have the reduction of the zinc, or the oxidation of the zinc, I should say, and the reduction of the iron. Okay, get a little confused there for half a second. So what I want to do is just break these up and put them into compartments. So let's start with the zinc. Let's pretend the zinc is here. We're going to put a piece of zinc metal. This is just a strip of zinc metal. We'll label it zinc. And in this compartment, we're going to put some zinc cation. Zinc 2 positive. Now realize that we can't put zinc by itself. Odds are we probably have a little bit of nitrate or something like that hanging out in there. Okay, so a little bit of nitrate or something. Anyway, in the other compartment, we're going to put in the iron. So we're going to put a piece of iron metal in here. Let me label that Fe. I know my handwriting isn't beautiful, so just pay attention. Fe. In solution here, we're going to have some iron cation, Fe3 positive. And we're probably going to have to put a little nitrate in there because otherwise that solution would be amazingly positively charged. Okay, the nitrate's just a spectator ion. It goes away. One thing I got to remind you of, in this reaction, a lot of students have, especially first year students, they think, hey, I have reactants, I blink my eyes, now I have products. That's not always the case. Sometimes reactions take a little bit of time. In this case, I want you to picture a piece of metal rusting or something like that outside. If that's the case, that piece of metal is out there for a long time before it turns into rust. Okay, so that's kind of why we're just setting up the reaction. All of these things are present. The reaction is going to take a while. What we do is, because there's a loss of electrons and a gain of electrons, we're going to take a piece of metal, a piece of wire, I should say, and attach it between the metals so that the electrons can leave the zinc and flow to the iron. So that's how the electrons are flowing. They flow from where they are lost, so here's our loss, to where they are gained. So there's our gain. If zinc is losing electrons, if that compartment is losing electrons, then that compartment's going to become positive. Okay, and the way it's becoming positive is, initially you have equal numbers of zinc 2 and nitrate in there, right? Well, what's happening is more of the zinc is becoming zinc 2. As this process happens, as this half reaction happens, you're going to create more zinc 2. So as the zinc 2 positive goes up, this whole thing is going to become more positive. On the flip side, over here, we have equal amounts of iron 3 and nitrate, creating a neutral solution. But as that puppy gains electrons, where are those electrons going? They're going down that iron metal, and every time an iron 3 cation bumps into it, it's going to suck up electrons. So iron 3 is going to iron, okay? Iron 3 is becoming iron metal, and so what happens is the nitrate is growing in number, so to speak, relative to the iron 3. So that thing is becoming negatively charged, okay? Well, you can't really have these strongly positive negative things because static charges can really build up. So what we do, and I'm going to try to squish it in here, is we're going to build in a little tube, and inside that tube we're going to put a slurry of potassium nitrate, which is potassium and nitrate. Alrighty, and I have little cotton plugs in there or whatever, okay, to kind of hold it back. What happens as let me just scribble that in there. That's potassium. That's nitrate. What happens as the reaction occurs, this is becoming positive, right? So what happens is the nitrate, being negative, will meander to that cell, that compartment. And the opposite is true for the right side. The potassium's positive, so it will move down to the negative. Opposites attract each other. You know potassium positive is called a cation. Well, guess why it's called a cation? because that is the ion in the bridge that's attracted to the negative cell. Well, that negative cell is called a cathode. Cathode came first. The cathode attracts positive ions. That's why the positive ions are called cations. Guess what the other one's called? You guessed it, anode. Anodes attract negative ions because anodes are positive, and so the negative ion was called an anion because it was the ion attracted to the anode. This guy is called an electrochemical cell. In particular, this is a galvanic cell, okay? But basically, this is the whole root of a battery. So what you have here are two half reactions separated. You can visualize, what if you broke this wire up and hooked something, electrical equipment in there and allowed the electricity to run through there? That's what the battery is kind of doing, It's using those electrons. More of that later. A prettier picture of this is right here. Okay, and my picture, one thing I failed to mention above is, hey, as zinc becomes zinc 2, what do you think happens to the mass of this piece of zinc? Okay, it's going to decrease. This side's going to lose mass. The piece of metal is going to lose mass, not the whole compartment. On this side of things, as iron 3 becomes iron, this guy's going to gain mass. And it's going to be plated with iron. It's one of the ways you can sort of plate things with a metal. As you put it as an electrode, let the metal plate itself on there. Alrighty? We don't always want to draw these big, giant diagrams. What we can do is make it one line of notation. And in line notation, you just look at your diagram. You got an anode, stuff in the anode compartment. You got crap in the cathode compartment and the cathode. Well, guess what? That's what we have. Anode, whatever's dissolved, cathode, dissolved, cathode. And so if you look at it, we go zinc 2 and zinc. So there's our zinc, there's our zinc. Zinc 2, zinc 2. Iron 3, iron 3. Iron, iron. Okay, is it always written that way? Sure. Positives are always written first, so the anode always comes first, cathode always comes second. Sometimes in the AP test, they flip that around just to mess with you. And you may ask yourself, but wait, what if I have an oxidation reduction reaction that doesn't have a solid metal in it? Well, here's one. I just flipped it around a little bit. Okay, if you looked at it, we have half reactions going on in which iron 2 is going to iron 3 and zinc 2 is going to zinc. So our oxidation, iron 2 to iron 3, is right here in the anode. And our cathode, our reduction, is right here. There's our zinc 2 and our zinc. All right, if we don't have a solid piece over here to clip a wire to, what we can use is this platinum electrode. Platinum electrodes have electrochemical potential 0. Don't worry about it. Anyway, platinum electrodes are what you use if you have to. You don't want to use them, but you can use them. And then in our line notation, you just throw the platinum out there because that's actually what is the anode. What's dissolved in the anode compartment? Iron 2 and iron 3. That's what we had there. So overall, you learned line notation. You learned how a redox reaction is becoming a galvanic cell. Hope you like it. Have a good time. I will talk to you later. This is Dr. Mandis signing off.